I found my QR codes. They were like sitting on my chair in my office, just on this and stuff. I was like, surely they couldn't be there, but they definitely were. They were missing in an obvious place. But the good news is I found them, so you can scan them to your heart's content to fill out the attendance form if that's the way you want to do it. Whatever you like. If you want them to, it might be hard for you to get this right here. Yes, can you see that okay? Ish. Can you see that okay? Okay, yeah. Let's see. Can I make it darker better? Kind of. Doesn't get less blurry, unfortunately. Okay. I know, I just hate like being in the dark. I think that actually looks okay. Am I mistaken?
Yeah, that's fine.
Okay. I'll also say the words, so I mean that should help as well. For those of you for everyone. So the plan for today is to go over the second practice midterm for Parlac, which is still, I'm sure, useful for people in the other class to see. It is relevant information that has lots of integrals that could come up at some time or another. And then if we finish that, we still have time left. We'll probably start going over some, I don't know, some Simpsons rule, trapezoid rule, maybe some basically the stuff we haven't gotten to yet. Maybe some more improper integrals. If people have questions, they're also welcome to ask them. So yeah. All right. It's 3:10. Let's get started. So here is the first. So this is just the beginning of the practice test. Feel free to ask questions along the way. So this first integral is the integral of x squared times cosine of 3x. I see a mixture. I see x to a power and a trig function. So I'm thinking it's either a u sub or integration by parts. I'm pretty sure it's not a u sub because there isn't really a good choice for u. If I pick u equal to 3x, the du is just 3 dx, and that's not going to do anything to take care of the x squared there. So I'm pretty confident it's integration by parts. So let's do integration by parts. So we're going to let u equal, let's see. If I use my LIATE, sorry, I forgot this is 21B, not 16B. If I use my LIATE acronym, LIATE, I don't have a log, I don't have an inverse trig, but I do have a power of x. So I'm going to let u equal x to that power. And then dv is going to be the rest, which is cosine of 3x dx. du is the derivative of x squared times dx, so that's a 2x times dx. V is the antiderivative of cosine of 3x, which is positive sine of 3x, divided by 3, or I would rather write times 1/3. So then we're going to use all that to get that our integral is equal to u times v, so that's x squared times 1/3 sine of 3x, minus the integral of v times du, which is 1/3 sine of 3x times 2x dx, which is going to require integration by parts again. Yeah. Sorry. So typically I would do this by pulling out any coefficients. So I'm going to rewrite this as x squared. Actually, I'm going to write it as 1/3 times x squared times sine of 3x. Minus, I'm going to bring out the 1/3 times 2 as a 2/3 integral of sine of 3x times x times dx. And now we're going to do integration by parts again. So for this new integral here, so for this integral here, we're going to let u equal the same type of thing. Still the any power of x, that's going to be x to the first. The dv is going to be the rest, which is the sine of 3x times dx. our du, the derivative of x is 1, so our du is 1 times dx. And our v, the antiderivative of sine of 3x is negative cosine of 3x divided by 3, or times 1/3, but I wrote divided by 3. So then what we're going to get, I feel like there's not quite enough space here to write this, but that's fine. We're going to get that this is equal to, we still have this first part here, the 1/3 x squared times sine of 3x minus 2/3 times the entire integration by parts for sine of 3x times x. So it's going to be the entire uv minus the integral of v du. So that's going to be our x times negative cosine of 3x over 3. I'm going to write that as negative 1/3 times x times cosine of 3x, just to make it a little bit more palatable, minus the integral of v du, which is negative 1/3 cosine of 3x. Sorry, that's a little smushed in there. I apologize for that. So here's what we've got, and here's what I would do. I'm going to rewrite this. I've got 1/3 x squared sine of 3x. And I'm going to distribute the minus 2/3. Minus 2/3 times minus 1/3 is positive 2/9 times x times cosine of 3x. And then I have a minus 2/3 times a minus 1/3. That's going to be a minus 2/9 times the integral of cosine of 3x dx. We probably could have done the integral right there. I know, yeah, I was, let's zoom way in here. Sorry about that. I know. I was trying to fit it in and it was not fitting in. So here's what we have again. We have the 1/3 x squared sine of 3x minus 2/3 times the entire uv minus the integral of v du. So there's our u times v, which is our x times negative 1/3 cosine of 3x, minus the integral of v du, which is negative cosine 3x over 3 times dx. And then I rewrote it a little bit. I still have this part here, the 1/3 x squared sine of 3x. And then this minus 2/3 distributes to each of these terms here. Minus 2/3 times minus 1/3 is positive 2/9 times x times cosine of 3x. And minus 2/3 times minus 1/3 is negative 2/9 times the integral of cosine 3x. Finally, sorry, I know I keep moving things around here. So finally we get 1/3 x squared sine of 3x plus 2/9 x cosine of 3x. And then the integral of cosine of 3x is sine of 3x over 3. So we're going to get a minus 2/9 times sine of 3x divided by 3 plus c. A bit much, kind of a challenging starter problem, but okay. If I had the space or the wherewithal, I would have simplified this to negative 2/27 times sine of 3x, but I don't think that's particularly necessary here. Unless the instructions say to simplify as much as possible, which they might. Let's see, reading the instructions here. Don't open the exam early. Make sure you have 8 pages. Write your name legibly on each page. Try to do your best to fit solutions into dedicated spaces. Okay. Close book, close notes. Show all work. Nope, this front page says nothing about simplifying answers at all. If I read the front page of this and it didn't say anything at all about simplifying answers, I would leave things as unsimplified as possible. Not to, or as unsimplified as I could without like doing extra work. Right? Like I'm not trying to expressly make it terrible looking. I'm just not trying to do any more math than I have to do while I'm taking this test. So yeah, so simplify reasonably is what I would say, but don't try to do any more than you have to. Okay. So let's look at this next problem. So I would also point out the amount of space given on a problem is often meant to be an indication as to how much work should be required. This next problem, not a lot of space. To me, it means it's probably going to be a one-step problem. So looking at this, natural log of x to the 7th power over 5x, I'm going to try a u substitution. I'm going to try letting u equal the natural log of x because du is equal to 1 over x times dx. And I could totally rewrite this integral. I would pull out the 1/5 in front and write it as, instead of natural log of x to the 7th over x, I'm going to write it as natural log of x to the 7th times 1 over x times dx. Because then it's really, really obvious to me that the 1 over x times dx is my du, and the natural log of x to the 7th is going to be a u to the 7th. So I'm going to have 1/5 the integral of u to the 7th du, which is a straightforward anti-power rule. So then we're going to get 1/5 times u to the 8th over 8 plus c. And then we do have to plug back in what u is equal to. You could leave it as 1/5 times natural log of x to the 8th over 8. But if we can see that 5 times 8 is 40, I would write it as natural log of x to the 40th, to the 8th power. Holy smokes. Sorry. That's why you don't simplify unless you have to, because you end up putting the wrong thing in the wrong place. Natural log of x to the 8th divided by 5 times 8, which is 40. Let's see. And that is an 8, despite how scribbly it looks. Sine cubed. Interesting. So we've dealt with powers of sine and cosine before. When you have a power of sine and power of cosine, when sine's to an odd power, or one's to an odd power, one's to an even power, you're going to let u equal the one that's raised to the even power, which you might notice isn't in this problem. Technically, there's a cosine to the 0th power there, and 0 is an even number. And it is the right choice to do a u substitution here, letting u equal cosine. It might be easier to see that if we did a trig identity first. So normally people first write this as sine of x, sine squared of x times sine of x times dx. And then they replace the sine squared with the trig identity 1 minus cosine squared. Because then it's a little easier to justify to yourself that we're going to let u equal cosine of x. Because there is actually a cosine of x, not a problem. So then we're going to let u equal cosine of x. Our du is negative sine of x times dx. So negative du is positive sine of x times dx. So we're going to rewrite this. We're going to rewrite it as the integral of 1 minus u squared in parentheses times sine of x dx, which is negative du. Now be careful here. Don't just write minus du because it looks like you're subtracting. If you want to write the negative on the du, write parentheses around it. Or better, what I would say is really better is to distribute the minus sign to the other two terms. So I would really prefer to write this as the integral of negative 1 plus u squared du. Right, just multiplying each term by negative. Yeah.
Could you print a negative like how?
You totally could do that as well. You could also write it as negative integral of 1 minus u squared du. Totally good either way. We integrate. If we do it this way, we're going to get negative u minus u cubed over 3. Let's see. Or if we'd done it this way, we'd have gotten negative u plus u cubed over 3, which if we distribute the minus sign would be the same. And then plugging in u equal to cosine, we're going to get negative parentheses cosine of x minus cosine cubed of x over 3. Let's see. Or if we distribute the minus sign, negative cosine of x plus cosine cubed x over 3. Let's see. For those of you on Zoom, you're welcome to ask questions as well. We're just looking over the second practice exam from Parlax's class. All right, continuing on. I made the, yeah, that's unfortunate. I think, yeah, I should use paper here. I printed this out double-sided, unfortunately, and I just think writing on this side is not going to look like it's going to be very easy to see if you can see through it. So let's use a different piece of paper. And I'll try to still use the amount of space I have as a guide, but I don't want you to struggle to be seeing what I'm writing. So That's not what I want. That's what I want. So let's look at this next one, which is the integral of e to the 5x cosine x. Okay. So seeing this should, I don't know, ring a bell. There should be something to note here, which is that we know that this is the kind of integral where you have to do integration by parts twice. The same integral shows back up, and then we add it back over to the other side, and then divide by 2 or divide by whatever the coefficient we happen to get. We're going to get a number not 2 here because of the 5x there. So let's do it. I should also look here just really quickly. There is this whole list of basic trig integrals that are given on the second page of the exam. So make sure that you at least glance over that before your test starts so that you're aware of what you already have given to you that you might not need to memorize. Oh, hyperbolic sine and cosine, that's weird. That's not something we've talked about in class. It's not that it's impossible, just that it seems weird you would put it on there unless you talked about it. So the nice thing about this is you can actually make either choice, meaning you could, I would pick u equal to the trig thing and dv equal to the rest, which is the exponential thing. But I will mention that if you happen to make the opposite choice for this specific integral where it's e to the something times cosine or e to the something times sine, if you were to choose u equal to e to the 5x and dv equal to cosine, it would also work out. So either way will get you there as long as you make the same choice both times. Okay. Our du is going to be negative sine of x times dx. Our v is going to be e to the 5x divided by 5. And I'm kind of wishing I'd done it the other way, but I should do it the way that I would typically do it, which is this way. So writing this out, we're going to get that our integral is equal to u times v. It's going to be 1/5 e to the 5x times cosine of x minus the integral of v times du. So e to the 5x over 5 times negative sine of x times dx. And then just like in the previous integration by parts that had to do more than once, I would bring any coefficients out in front. So I'm going to rewrite this as 1/5 e to the 5x times cosine of x plus 1/5 integral e to the 5x times sine of x. And then I'm going to do integration by parts again, making the same type of choice. So since I chose u equal to the trig function the first time, I have to choose u equal to the trig function the second time. Otherwise, things will not work. Otherwise, you'll end up getting the same thing you started with, but like just the original integral equal to itself, which is true, but not. So letting u equal sine of x this time, and dv equaling e to the 5x dx, our du is positive cosine of x dx, and our v once again is e to the 5x divided by 5. So now we're going to write this out again. We're going to get 1/5 e to the 5x. Sorry, I missed an x there before. 1/5 e to the 5x times cosine of x plus 1/5 times the entire uv minus the integral of v du. So we're going to get e to the 5x over 5 times sine of x minus the integral of e to the 5x over 5 times cosine of x dx. And here's where I would probably start showing less work as a student. So I want to show all the work because I'm showing you all how to do it, but let me show you what I would really do if I was doing this. I would say that on the left-hand side, I have the integral of e to the 5x cosine of x dx, and it's equal to 1/5 e to the 5x cosine x plus 1/5 times 1/5 is 1/25 e to the 5x times sine of x. And then 1/5 times 1/5 is a minus, because the minus sign there, 1/25 integral of e to the 5x cosine x. I add that to both sides. 1 of a thing plus 1/25 of a thing is 26/25 of that thing. So we have 26/25 of our integral is equal to that stuff there. And then I would say that our actual, I'd skip that step kind of. Our actual integral of e to the 5x cosine of x dx is equal to the reciprocal of this. So 25/26 multiplied by the thing under the braces there, over the braces there, which is 1/5 e to the 5x cosine x plus 1/25 e to the 5x sine of x plus c. I probably showed too much work for a test, to be really frank. There's probably, you could probably do less work showing than I have done. Can you? Yeah, maybe. I don't know. Maybe not. It's kind of hard to say. So for this kind of problem, though, there's a lot of steps. So just take it slow, be careful. Yeah, know what to expect, right? You know that if you see an e to the something times x times cosine, or e to the something times x times sine, it's this process. Yeah. Which to me, I don't feel like there's enough room. I would struggle to fit that all into this space here. What's that? Which one? I'm not sure what you're saying exactly. I'm sorry. You just wanted to see the rest of it? So looking at the next, which is much less terrible, we have the integral of x to the 4th times sine of x to the 5th. To me, this one seems very straightforward. I hope it does seem straightforward to the rest of you as well. This is going to be a u substitution, letting u equal the inside or the argument of the sine function. For du is going to be 5x to the 4th times dx. 1/5 times du is going to equal x to the 4th times dx. So we can rewrite this as the integral of, if I don't want to do too much writing, I'm going to say that that part there, that's my 1/5 du. So I'm going to get sine of u times 1/5 du, which is going to end up being 1/5 times the antiderivative of sine of u, which is negative cosine of u, plus c. And then I would rewrite this as negative cosine of x to the 5th divided by 5 plus c. Something I noticed about these exams is each of these questions is worth very few points. Right? Like the whole test is out of 30 points. Each question's like worth 3 or 2 points. So each question is meaningful, but like if I was trying to get through this test, I might skip problem D and do problem E first, because I know I can do problem E fast. And I know I can do maybe F. F's a little weird, but right, maybe not that you should necessarily skip D because it's not particularly hard, it just takes time. But do the things you know you can do quickly so that you can get all the points that you can get. Also, and also looking at this, like I saw that the last page of this exam was worth 2 points and it was 2 problems. So I might like use your time wisely. Try to get the most points you can. All right, let's look at F, which is a little bit funky. I guess that's why it's letter F. So negative 3x plus 7 over x squared plus 9, the integral of that. Oh, man. How do we approach this? Well, I know what the answer is. I'm trying to think about how I would think about this. So if you see an irreducible quadratic factor, like x squared plus 9, normally that shows up like in a partial fractions kind of problem. But it's not really partial fractions because there aren't any other factors. And x squared plus 9 doesn't factor. That's why it's called an irreducible quadratic factor. It does not reduce to linear factors. And I know it's been a little while since we did an example, but when we did an example where we had an irreducible quadratic factor in our integral, when we got to this part where we had like a bx plus c over the irreducible quadratic factor, and we were integrating that, you had to break it up into the bx over the thing and the c over the thing. So what I'm saying is if you have some linear thing over x squared plus 9 or x squared plus 1 or x squared plus 16 or x squared plus something positive, the only way to deal with this is to break it up into 2 intervals. 3x over x squared plus 9 and 7 over x squared plus 9. One of these will always be a u sub, the one that has the x on top. Okay, so that's always going to be a u sub. The second one's always going to be an inverse tangent. And because she's giving you the formula on that second page of the test, you don't have to worry about memorizing the formula. So let's do the u sub part first. For the u sub, we're going to let u equal x squared plus 9. Or du is 2x dx. I don't have 2 times x, so let's just get rid of the 2 or divide by 2. So 1/2 du is equal to x times dx. So, and I do want to write this as 2 integrals. So I've got the integral of negative 3x over x squared plus 9 dx plus the integral of 7 over x squared plus 9. So that integral, the integral of negative 3x over x squared plus 9 is going to be negative 3 times the integral of x over x squared plus 9. And then that's going to become negative 3 times the integral of, so the x dx is going to be 1/2 du, and the x squared plus 9 is going to become u, and that's just going to end up being negative 3/2, and the integral of 1 over u is the natural log of the absolute value of u. So we end up getting negative 3/2 times the natural log of the absolute value of x squared plus 9. That's what that first part is equal to. And then the second part, which I've really smartly not left myself enough room for here. Squeeze out some room here. So for the integral of 7 over x squared plus 9, we're going to refer back to the formula sheet. It says the integral of dx over a squared plus x squared is 1 over a arctangent of x over a. So what we're integrating here is we have 7 times the integral of 1 over 3 squared plus x squared. And using the formula, that's going to be 1 over 3 arctangent of x over 3. We get 7 times 1 over 3 times arctangent of x over 3. And so then our final answer, which I know I've kind of done this very kind of piecemeal here, is our actual answer is that the integral of negative 3x plus 7 over x squared plus 9 is equal to negative 3/2 natural log of the absolute value of x squared plus 9 plus 7/3 arctangent of x over 3 plus c. And yes, that is always the way we deal with a linear function over x squared plus a constant. You always have to break it up into these two pieces. The piece with the x on top will always be a u sub. The piece with the constant on top will always be using this arctangent formula. I would say it's more likely usually to pop up when you're actually doing partial fractions. Like in the next, well, it's not going to pop up in the next problem. The next problem, I think, is a partial fractions problem. So any questions about this one before we move on to the next one? I would point out, just as an aside here, you would do, for example, the integral of 4x plus 1 over x squared plus 25 would require the same process. Sorry, you can't see anything I'm writing, apologies. Would require the exact same type of steps. Yeah, I'm not going to do it, but good practice. All right, so let's look at the next one, which I can use this next page, so sure, why not? So the next integral is the integral of x plus 1 over 2x squared plus 3x minus 2. And if I was looking at this problem, I would first at least consider a u substitution. So I would think, okay, let me try u equal to 2x squared plus 3x minus 2. I wouldn't actually probably write it down, but I would try it in my head. And I say, okay, well, the derivative of that's going to be du is going to be 4x plus 3. And oh, if only that was a 4x plus 4, it would totally work. Because 4x plus 4, I could factor out the 4 and I have an x plus 1. So if you can do a u sub and your du is a multiple of the numerator, that's all steam. I'm trying to think of like go forward, all thrusters forward. I don't know. I'm trying to say something like go forward, move ahead. That's the right path to take. But clearly the words are not going to. So, but that's not what's happening here because we have an x plus 1, not a 4x plus 3. So instead, well, that doesn't look great. It doesn't look great at all. Because if I was going to use partial fractions, it looks like it might meet the criteria. It's a rational function. The degree on top is smaller than the degree on the bottom. Does the bottom factor? Maybe, but it looks a little challenging. So here's the thing I would think about if I was trying to factor the bottom. I'm hopeful that at least one of the factors is just like an x plus something or an x minus. And the way you can check that is by checking if any of the factors of that constant term, -2 in this case, are zeros of your polynomial. So if I look at 2x squared plus 3x minus 2, I'm going to try plugging in x equal to plus or minus 1 or plus or minus 2. And I can see that 1 and -1 both aren't going to work. So if I plug in 1, I get 2 plus 3 minus 2, which isn't 0. It's -1. It's 3, sorry. If I plug in -1, I get 2 minus 3 minus 2, which also isn't 0. If I plug in positive 2, I get 8 plus 6 minus 2, which isn't 0. But if I plug in -2, I get 2 times 4 plus 3 times -2, which is -6, minus 2, and that is 0, which means that x minus minus 2 is a factor. So this should factor as x plus 1 over x minus minus 2. And then we can figure out the other factor based on the fact that x plus 2 times whatever is over here has to multiply to 2x squared plus 3x minus 2. So you have to have a 2x and a minus 1. And it does work. There are other ways of factoring this quadratic. This is just the way that seemed fastest to me. But if you have a different method that works for you, great, use it. And then it's definitely a partial fractions problem. So we're going to say that x plus 1 over x plus 2 times 2x minus 1 is equal to a over x plus 2 plus b over 2x minus 1. We're going to multiply both sides by our common denominator, which is x plus 2 times 2x minus 1, to get on the left-hand side x plus 1. On the right-hand side, a times 2x minus 1 plus b times x plus 2. I would always encourage using the method of convenient values of x. So I'm going to pick x equal to -2, because that's going to make one of those terms 0. If x is -2, we get -1 on the left. We get a times 2 times -2 is -4, minus 1 is -5. We get b times 0. So we end up getting 1/5 is equal to a. My other convenient value of x is positive 1/2. So if x is positive 1/2, then we're going to get 1/2 plus 1, which is 3/2 on the left, equal to a times 0. That's why we're picking 1/2, because 2 times 1/2 is 1, and 1 minus 1 is 0. Plus b times 1/2 plus 1, which is 5/2. Solving for b, 3/2 divided by 5/2 is 3/5 equal to b. Just to make sure everyone's okay with that, right? 3/2 divided by 5/2 is 3/2 multiplied by 2/5, and the 2's cancel, and you get 3/5. But whenever you divide a fraction by a fraction, if the denominators are the same, they just cancel out. So then we rewrite our integral as the integral of 1/5 over x plus 2 plus 3/5 over 2x minus 1. The integral of I'm really not thinking of that 1/5 being there. I'm thinking of this as 1 over x plus 2. The 1/5 is just a constant multiple. So I'm going to get 1/5 times the integral of 1 over x plus 2 is the natural log of the absolute value of x plus 2. Same deal here. I'm not thinking of this as 3/5 over 2x minus 1. I'm thinking of this as 3/5 times 1 over 2x minus 1. And my integral is going to be 3/5 times the integral of 1 over 2x minus 1, which is the natural log of the absolute value of 2x minus 1, divided by 2. Because if you took the derivative of the natural log of 2x minus 1, you would get 1 over 2x minus 1 times the derivative of 2x minus 1, which is 2. And that 2 needs to get canceled out by the 1/2 that's right there. So whenever you integrate something and you have not just x, but a multiple of x, you almost always end up dividing by the coefficient of x. Plus c. All right. Looking at the next one. Show that the integral of 1 over the square root of 4 plus x squared is equal to the natural log of the square root of 4 plus x squared plus x over 2 plus c. And they tell us what to do. They tell us hint. I feel like hint is not a strong enough word. The word should be do this. Use a trig sub and then formula 14 from the table of basic integrals. So we'll start with the trig sub. So I see a 1 over the square root of 4 plus x squared. And I know that when it's a plus, I'm going to use a tangent as my trig sub because plus looks like t and tangent starts with t. I mean, literally, that's what I actually think of when I do this. Okay. So we're going to let x equal not just tangent theta, but something times tangent theta. What do we have to multiply by tangent here? Good question. Here's what we want to happen. We want the 4 plus x squared to turn into a trig identity. We want 4 plus x squared to become 4 plus 4 tangent squared theta, so that then we can factor out a 4 and have 1 plus tangent squared theta, which is equal to secant squared theta. That's always the goal with the trig sum, is that the substitution you're making, the stuff inside the square root, becomes a nice trig identity that just has one term instead of 2 terms added together. So to make this happen, it looks like x squared has to be 4 tangent squared, so x better be 2 times tangent theta. The coefficient here is always just the square root of that constant there. And then we also have to find dx. dx is equal to the derivative of 2 tangent theta, which is 2 secant squared theta, d theta. And then we rewrite our integral, kind of like when we do a u sub, every x has to turn into a theta thing. Just like with a u sub, every x has to turn into a u thing. And I think the safest route here, so that we don't make any mistakes, is literally just to replace each thing with what we said it's equal to. So I'm going to get 1 over the square root of 4 plus, I'm replacing x with 2 tangent theta. I'm replacing dx with 2 secant squared theta d theta. And then we have to simplify a bit. So we're going to rewrite this as the integral of, I'm going to put the 2 secant squared theta on top. And on the bottom here, well, I can see that that's 4 plus 4 tangent squared theta. I'm going to factor out the 4 and write it as the square root of 4 times 1 plus tangent squared theta, d theta. And now you can kind of choose how much work you really want to show. 1 plus tangent squared is secant squared. So I think it would be legitimate to, from this point, get rid of the square root and say that this is equal to the integral of 2 times secant squared theta, d theta, over the square root of 4 is 2, the square root of secant squared is secant of theta. And most of the stuff cancels, and we're left with the integral of secant theta, d theta, which is given, but I feel like we've talked about it enough that I think you all probably know what it is. The integral of secant theta is going to be the natural log of the absolute value of secant theta plus tangent theta. plus C. Which I will say is, do I still have it? I've lost it clearly. There it is. So if we look over here, right, equation 14 is exactly that. The integral of secant of x is the natural log of secant x plus tangent x. Absolute value of that. Make sure you use the right variable though. We're using theta here. So you should write secant theta plus tangent theta. Do make sure when you do a trig sub that whatever you do, when you write x equal to whatever, you can't say it's 2 tangent of x. You can use literally any other letter or Greek letter. I would say theta is the natural choice. But whatever you pick, make sure you pick something different than the variable you're already using. Otherwise, things get weird. We can't stop here because that answer doesn't look like the answer that we said we're supposed to get. So this is the time where we have to draw the triangle. That's what I like to say. So we have that. We can make this fit, yeah. We have that x is equal to 2 tangent theta, which I would then isolate tangent and say that tangent theta is equal to x divided by 2. This is where you have to know your sides of your trig triangle stuff. Or as I would say, you have to know your SOHCAHTOA, which is not my favorite acronym, but it's, so I know that tangent of an angle is equal to the opposite side of that angle divided by the adjacent side of that angle. So since tangent of theta is equal to x over 2, the side opposite theta is going to be x, and the side adjacent to theta is going to be 2. And the third missing side, we could use the Pythagorean theorem to find. Let's call it C, and we're going to say that 2 squared plus x squared equals c squared. And then if we just take the square root of both sides, the square root of 4 plus x squared is equal to c. Or you could just know that the missing side is always going to be the square root in your integral that made you start this process in the first place. Always, always, always. I can't say it enough. Always. So that third side is the square root of 4 plus x squared. And then we use this triangle to figure out what these two things are. So this is going to equal. So here's what you could do really if you wanted to. You kind of cheat and see like, well, I know it's supposed to be that. I've drawn the triangle. So I could just write the natural log of all that. But I'm not. I would say that the secant theta is, well, I know that secant's the, I don't remember what secant is. Like maybe I actually know this, but I used to not remember what secant was. But I did know that secant was the reciprocal of cosine, and cosine is the adjacent over the hypotenuse. So cosine of theta is 2 over the square root of 4 plus x squared. So secant of theta is the square root of 4 plus x squared over 2. It's the hypotenuse over the adjacent. That's going to be the square root of 4 plus x squared over 2 plus tangent of theta is opposite over adjacent, which is x over 2. I think it'd probably be fine to leave it like that, but if you really, really wanted, you could then write it as the natural log of the absolute value of one fraction, square root of 4 plus x squared, plus x all over 2. Let's see. But I don't think you really probably need to do that last step because it should be obvious that that's the same as that. Okay. All right, I'm just going to keep going. Stop me if you have questions. Let's look at this one here. Might need some paper here. So let's read the very bold capitalized instructions here. In problems, I feel like I'm being yelled at. In problems 2, 3, and 4, you need to show all your work and simplify your answer as much as possible. Okay, so there's some simplifying that we actually have to do. All right. So problem 2, worth 3 points. But again, 3 points is 10% of this exam. So don't look at the 3 and be like, oh, it's not that much. It's still a significant amount of points. Find the volume of the solid generated by revolving the region enclosed by y equal to the square root of 3x and y equals 2 and x equals 0 about the x-axis. Simplify your answer. I think whenever you do a problem where you're revolving, you probably should draw the region. There's no way around it. Drawing the region is the easiest, fastest way to figure out what's going on. So it doesn't have to be perfect. I've got y equal to the square root of 3x, which, okay, looks kind of like a square root function. I've got y equal to 2, which is a horizontal line. Okay, we can say that's horizontal. And we've got x equal to 0, which is the vertical y-axis. Be careful. People tend to mess that up. So over here, there's my x equal to 0. The region we're looking at should be bordered by all of these things. So it's got to be this little section right here. Great. And we're revolving this around the x-axis. I will point out, it has not been specified what method we have to use. We could do whatever we want. We could use a vertical strip if we care to, or a horizontal strip if we care to. And either one is, in my opinion, a valid choice here, because a vertical strip, the bottom of the strip is always this square root function. The top of the strip is always this y equals 2 function. Or if I drew a horizontal strip, the left side of the strip is always x equal to 0. The right side of the strip is always this square root function. So as long as the ends of your strip are always the same, no matter how high or low you draw, or no matter how far left or right you draw, either choice is good. So since either choice is good, I'm going to make the choice that requires the least amount of work, which means I don't want to change functions if I don't have to. So since everything is already written as a function of x, I want to keep things in terms of x, meaning I want to use a vertical strip so that I have a dx. So we're going to do the vertical strip. I could also do it the other way if you all want me to, but let's do it this way first. Here's my vertical strip, and I will point out that my strip is perpendicular to my axis, which means we have to use the disk or the washer method, depending on what we have. I will also point out my strip doesn't touch my axis of rotation when I draw it. So that means it's got to be the washer method, because we're missing some inner circle. So trying to do as little work as possible, I would say, well, the volume of my washer very generally is pi. Well, in fact, and it's the formula is given here. It's pi times the integral of your big radius minus little squared. So that's what I would write. It's pi times my big radius squared minus my little radius squared times dx, which in this case is going to be pi times my further away function is y equal to 2. My closer function is y equal to the square root of 3x. So it's going to be 2 squared minus the square root of 3x squared dx. I should note, and I do think this is generally kind, is that on the exam here, all the formulas are given, and they are given with the correct variables for the way this is set up. This one, if you did it in terms of x, it would be disk or washer. If you did do it in terms of y, it would be shell. And they've given you the appropriately correct variables for each method, depending on how we're doing it. So that is a kindness. They could have just easily said d whatever here and not been so explicit. So that's good to know that when you're looking at that, at least they're giving you the right thing, depending on how you want to do it. And then we do have to finish this completely, right? Because it says find the volume. So then we're going to do the total volume is the integral from as far left as 0 to as far right as, oh, what is that point right there? Well, it's when this function and this function cross each other. So I guess you have to set this equal to each other. So if I set the square root of 3x equal to 2, I'm going to square both sides. And then x is going to equal 4/3. So my limits of integration here are from x equals 0 to x equals 4/3. The pi is on the outside. And then I'm going to get 4 minus the square root of 3x squared is just 3x. This integral is not terrible, right? It's about as easy as they get as far as the actual execution here. Integrating, we get 4x. Oh, sorry. Don't make the mistake I'm about to make. We get pi times 4x minus 3x squared over 2 from 0 to 4/3. And that's going to end up equaling pi times 4 times 4/3 minus 3 times 4/3 squared over 2 minus 0 minus 0. I would probably stop here. Even though I know the problem says simplify as much as possible, I would stop here and go on and do other things. And then if I have time at the end, come back and do the simplification. Yes, I know it's worth points. And depending on your perspective, maybe it's really easy for you to do this. Maybe it's not. So coming back after we've done all the other things I've got pi times 4 times 4/3 is 16 thirds. And then 3 times 4/3 squared, if I'm smart about this, I'm going to say that's 3 times 4/3 times 4/3. So that instead of multiplying it out, I can just cancel it. And then 4 times 4/3 is 16 thirds. So check this out. I have pi times 16 thirds minus 16 thirds divided by 2. There's an easy way to do this. I have a thing minus half of that thing. If you have a whole something and take away half of it, how much are you left with? The other half of it. So this is going to equal pi times 16 thirds divided by 2, which is 8 pi over 3. You could also do more math here to figure it out, but I really like doing it that way. You could also, another way to think about what I just said in a more mathematical way is you could say that this part here is pi times and then factor out a 16 thirds. And then you're left with a 1 minus a 1/2. And then you have 16 thirds times 1/2, which is 8 thirds. Cool. I like that. All right. The papers are all yours. Problem 3. Find the area of this. I've got this here. Let's just do this. Let's refocus here. So this question says, find the area of the surface generated by revolving x equal to y cubed over 3, where y is between 0 and 1, about the y-axis. Simplify your answer. And then they give you a hint, or give you the formula. The area of a surface generated by revolving x as a function of y around the y-axis. This is one of the correct formulas to use. I don't imagine she would give you the one that's less good to use. So there is another formula that would work, right? You can also do it as the integral from whatever to whatever of x times the square root of 1 plus solving this for y in terms of x, the derivative of that squared. Don't try to make life harder on yourself, right? If she's giving you something in a certain way and say, here is the formula, follow the path of least resistance. So we're going to plug in what we've got. My f of y is y cubed over 3. That's what x is equal to, f of y. So my f prime of y is very nicely 3y squared over 3, which is just y squared. So my area is going to be 2 pi, I should say my surface area, but okay. 2 pi times the integral from y equals 0 to y equals 1 of the square root of, oh, I forgot the f of y here, sorry. My f of y, which is y cubed over 3 times the square root of 1 plus y squared dy. And now if we simplify just a tiny bit, I'm going to bring out the 1/3 and write this as 2/3 pi integral from 0 to 1 y cubed times the square root of 1 plus y squared is y to the 4th. That's looking like a real good u substitution, right? It's screaming u substitution. Let u equal the stuff inside the integral, inside the square root. I mean, it should also be inside. So we're going to let u equal 1 plus y to the 4th. Our du is 4y cubed dy. I don't have a 4, so I'm going to say that 1/4 du is equal to y cubed dy. And I'm also going to change the limits of integration. So if y is equal to 0, u is going to equal 1 plus 0, which is 1. If y is equal to 1, u is going to equal 1 plus 1 to the 4th is 1 plus 1, which is 2. So those are our new limits of integration, which means we won't have to change back. So we're going to rewrite this as 2/3 pi times the integral from 1 to 2 the y cubed dy is going to become 1/4 times du. I put the 1/4 on the outside. And the square root of 1 plus y to the 4th is going to be the square root of u, which is u to the 1/2. So we're going to integrate. This 2/3 pi times 1/4 is really 2/12 pi or 1/6 pi. And the integral of u to the 1/2 is u to the 3/2 divided by 3/2 or times 2/3 from u equals 1 to u equals 2. 1/6 times 2/3 is 2/18 or 1/9. So we get pi over 9 times 2 to the 3/2 minus 1 to any power is just 1. So 1 to the 3/2 is 1. And that's as good as it gets. 2 to the 3/2 is unfortunately not any nicer than that. I mean, if you really, really wanted, you could say it's pi over 9 times 8 to the 1/2, which is the square root of 8 minus 1. I don't think that's making it any better. Right, 2 to the 3rd is 8, and the square root of 8 is. All right, good times. Do you have to change? You do not have to change limits of integration. So let's pretend like we hadn't changed limits of integration for a second, just to kind of show that as well. So let's say we did this, and we said, okay, I don't want to change the limits, but I am doing the u sub. So I'm getting 2/3 pi times 1/4 integral, still from x equals 0 to, from y equals 0 to y equals 1 of the square root of u du. And then that's going to be, well, again, that's still a pi over 6. The integral of u to the 1/2 is still 2/3 times u to the 3/2 from, I do think you need to write y equals 0 to y equals 1 here, though, so that the person knows that you didn't change the limits of integration and that you're aware that you didn't change them. And then simplifying further, pi over 6 times 2 over 3 is pi over 9. And then we plug back in the fact that u is equal to 1 plus y to the 4th. So we end up getting 1 plus y to the 4th to the 3/2 evaluated from y equals 0 to y equals 1. And then we can plug in and get pi over 9 times 1 plus 1 to the 3/2 minus 1 plus 0 to the 3/2, which is the same answer we got before. And again, I would simplify. I would not write 1 to the 3/2. I would write pi over 9 times 2 to the 3/2 minus 1. Yeah, if you don't want to change them, that is totally viable. You can do it this way. I think changing them is the better way to go, but if you don't want to, that's also fine. Okay, let's look at number 4 here. Find the length of the curve y equal to the natural log of 5x minus x squared over 8. X is between 1 and 3. So my guess here, yeah, that'll work out okay. My guess is that the thing that usually happens is going to happen here. What do I mean by that? I mean that when we find our f prime and square and add 1 to it, we're going to end up getting something where f prime squared is going to have a negative 1/2 in the middle. We're going to add 1 that's going to change that to a positive 1/2. And then the whole thing is going to factor back essentially the same way that it already did, just with a change sign in the middle. Let's do the work to see. And the natural log of 5x, there's a little bit of a red herring, I feel. So our f of x is the natural log of 5x minus x squared over 8. Our f prime of x is 1 over 5x times 5 minus 2x over 8. We definitely want to simplify this. That's equal to 1 over x minus x over 4. And if I square that, my f prime of x squared is 1 over x minus x over 4, quantity squared. And if I multiply that out, that's going to be 1 over x squared minus 2 times 1 over x times x over 4 plus x over 4 squared, which is x squared over 16. And look at that middle term there. The middle term is exactly -1/2, which we expected to happen. Okay, so let's find the length now. Oops. So the length here is going to equal the integral from x equals 1 to x equals 3 of the square root of 1 plus, I already did all this work over here. I shouldn't do it again. So what I should do is I should just say, well, look, I've clearly written that f prime of x squared is equal to that. So let's just put that in for f prime of x squared. So good rule of thumb, don't repeat work that you're turning in. But then that's going to equal the integral from 1 to 3 of the square root of 1 over x squared plus 1/2 plus x squared over 16. And because we can see that 1 over x minus x over 4 quantity squared ends up being 1 over x squared minus 1/2 plus x squared over 16, it's not a big leap to see that the insides here factor as 1 over x plus x over 4 quantity squared. This is the pattern that happens a lot of the time with these arc length. And then the square root of this squared, you can just get the stuff inside. Technically, it should be the absolute value of 1 over x plus x over 4. But since x is already always positive, right? X is between 1 and 3, we don't need to worry about that. So we're going to get just the integral from 1 to 3 of 1 over x plus x over 4. We integrate, we get the natural log of the absolute value of x, which again isn't super necessary, but fine to write, plus x squared over 8 from 1 to 3. So it took a really long journey to get almost exactly back to the same function we started with, without the 5. Okay, that's the 5 that there is in kind of weird. And then we plug in and we get the natural log of 3 minus 3 squared over 8 minus the natural log of 1 minus 1 over 8. And simplifying this as much as possible, because that's what the instruction said, natural log of 1 is 0. Negative 9 over 8 plus 1 over 8 is negative 8 over 8, which is just negative 1. So this simplifies pretty nicely to the natural log of 3 minus 1. All right. And then there's these last two problems, I think. Last two? Can I find them? Maybe. Oh, they're on the back of this page here? Yes, they are. I can find them. Okay. So let's read, let's zoom out so we can see the things. So let's read through these problems here. So 5 says, let R be the region in the plane enclosed by the curves y equal to x and y equal to x to the 10th. Let S be the solid obtained by revolving R about the x-axis. Find the definite integral that can be used to compute the volume of S using the washer method. Sketch R and a few segments in R that generate the washers. Okay. So I would say sketching R is the first thing we should do. So the region here, y equals x, and between y equals x and y equals x to the 10th. So y equals x is not too terrible. It's like this. Well, it's kind of like that. Sorry, that's not my best rendition here. And y equals x to the 10th is going to be something that intersects it at the point 1, 1. It kind of comes up beneath it. So it's going to do something kind of like this. So there's my not very good drawing of that region there. When you have y equals x to a higher power than 1 and y equals x, they always intersect at the origin and at the point 1, 1. And the one that's to a higher power is the one that's always going to be the lower function. So I was going to draw this in a more exaggerated way to kind of help me see what was going on, and just better because I didn't draw it very well the first time here. I would draw it maybe kind of like this. Help me see what was going on. So here's my region, which color in lightly here. And then it says to sketch R and a few segments in R that generate washers. And we're going around the x-axis. So let me ask all of you, my segments that generate washers, should they be vertical segments or horizontal segments? Or as I would say, strips or cross sections? Should my strips be vertical or should my strips be horizontal? Yeah, vertical. Because I know that for the washer or the disk method, my strips have to be perpendicular to my axis of rotation. I would draw one, but I guess you said draw a few. Okay. So there's my strips that generate the washers. So then the volume here is going to be the integral from 0 to 1 of pi times my large radius squared. My large radius is the function that's further away, which is y equal to x, minus my smaller radius squared. My smaller radius is the function that's closer to the axis of rotation, which is x to the 10th. And I would write it this way. I would not simplify. Because you're really being asked to express this so that you know what's going on. And then, of course, yes, then we're being asked to do it using shells. So same kind of deal. We're going to draw the same region. But now, we're still going on the x-axis and we want to use the shell method. Now our strips or segments have to be parallel to the axis of rotation. Which means we're going to be using dy for sure. And the volume of my shell is equal to 2 pi times my radius times my height times dy. My radius is how far the strip is from the axis of rotation, which is y in this case. And my height is just how long the strip is. So my radius here is y. My height is the right function minus the left function in terms of y. So this function that was y equal to x is now x equal to y, which is not really a big change. And this function that was y equal to x to the 10th is now x equals y to the 1/10, which is a change. All right, so now the right function, this is again why drawing it is really necessary here. To know which functions on the right or the left, the easiest way is just to have drawn them. So our volume of our shell, actually just write the whole volume. The volume is going to be 2 pi times the integral of my radius, which is y, times my height, which is the right function, y to the 1/10, minus the left function, which is y, dy. And I will point out our limits of integration are numerically the same, but they're not from x equals 0 to x equals 1. They're from y equals 0 to y equals 1. Which isn't super important, but it's important that they're different because if they intersected somewhere else like 2, 4, then it'd be important that you went from instead of x equals 0 to x equals 2, y equals 0 to y equals 4. So just make sure that you get the correct values there depending on what variable you're using. And that's all we would write there. All right. So, anything you would like to ask about? Questions? We have 13 minutes left. Feels like starting a new thing with 13 minutes left might not be the best use of our time. So let me instead What's missing? I'm trying to think of if there's anything that I didn't see on this exam that I would have asked about. Pretty, I feel like this is a pretty comprehensive exam. Like I feel like it hit kind of all the highlights. There were partial fractions. There was integration by parts. There was U substitution. There was certainly a trig substitution. There's a repeated integration by parts. Yeah, I mean, it feels like it's hitting all the highlights. Yeah, totally. Yes. Yeah. So let's do this one. So let's say we wanted to find integral of, let's not make it too terrible. X squared plus 2x over sure. X squared minus, oh, I don't love that choice already. Sorry, I'm making bad choices here. I'm gonna start over. Apologies. I know it's terrible when people do that. Let's do this again. Let's try this. The integral of x minus 2 over x squared minus x times x squared plus 1. Which I would normally multiply out to make it even harder, to make you have to factor it, but okay. So, yeah, that's fine. So we're going to write this as x minus 2 over, I'm going to factor the bottom as completely as possible. And I can factor out an x from the x squared minus x. So I have an x times x minus 1 times x squared plus 25. And I'm going to write this as a over x plus b over x minus 1 plus cx plus d over x squared plus 25. So whenever you have an irreducible quadratic factor like that, you have to have a linear thing on top of it, a cx plus d or a whatever letter times x plus whatever the next letter is. Usual process. We multiply both sides by our common denominator. So on the left-hand side, we always just get the numerator. On the right-hand side, a over x times that, the x's cancel. We get a times x minus 1 times x squared plus 25. Plus b times the x minus 1's cancel, you get x times x squared plus 25. Plus the quantity cx plus d in parentheses times x minus 1. And again, just like last time we had a partial fractions problem, I'm going to start by using the convenient values of x, which are 0 and 1. Those are the only convenient values of x. So that x equals 0. I get negative 2 on the left. I get a times negative 1 times 25 plus b times 0 plus cx plus d times 0. So I really just get negative 2 equals a times negative 25. So a is equal to 2/25. And then we go ahead and find b. Or sorry, we don't find b. We do the next convenient value of x, which might give us b and might not. So we plug in x equal to 1, and we get 1 minus 2 is negative 1 equal to a times 0 plus b times 1 plus 25 is 26. That's interesting. And then, yeah, we're going to get negative 1 over 26 equal to b. The reason I say that's interesting is because most of the time when you do problems like this, your constants often have like the same denominator, or they're not, and not that we couldn't get a common denominator here, but like it would be a bit of work to do that. So it's a little atypical from my perspective, but that's fine. That happens when you make up a problem out of the blue. Yeah, just double checking that the work is right here. That's right. Okay. And then we've run out of convenient values. So then we start doing what I call equating coefficients. So looking at the right-hand side of this equation, if we were to multiply things out, what would the highest power of x be? I think it'd be x to the third. Okay, so I'm going to think about x to the third. On the left-hand side, there isn't any. On the right-hand side, if I multiply this out, I am going to do it a little bit. So if I multiply just this part out, it's going to be x cubed minus x squared plus 25x minus 25. This part here would be x cubed plus 25x. And this part here would be x squared minus x. So I'm looking at the coefficients of x cubed. I'm going to get an a times x cubed, a b times x cubed, and a cx times x squared will give me a c times x cubed. So it looks like 0 is equal to a plus b plus c, which is going to be kind of terrible, but oh well. So it looks like c is going to equal positive 1/26 minus 2/25, which, yeah, is a terrible. I mean, okay, we can get the common denominator to be 25 minus 2 times 26 is 52 all over 26 times 25, which is negative 27 over 26 times 25, which is 650. Okay, I've seen nicer numbers, but whatever. And then we'll do the same sort of thing to find D. I would point out, if someone actually gave you a problem like this in your test, the numbers would have been thought out better to come out less terrible. So we're looking at the next highest power of x, which is x squared. On the left-hand side, still 0x squared. On the right-hand side, I would have a times a negative x squared, so I'd have a negative ax squared. I wouldn't have a b times x squared. I'd have a b times x cubed and a b times 25x, but no b times x squared. I would have a c times x squared because I'd have c times x times negative x, so I'd have a negative c times x squared. And I would have a d times x squared. I'd have d times x squared as well. So then it looks like 0 is equal to negative a minus c plus d. So it looks like d is equal to a plus c. So d is going to equal c, which is negative 27 over 650, plus c, which was, sorry, plus a, which is 2 over 25. Interesting. Okay. Which I think ends up being nicer than it looks. I feel like D is the same as B somehow, or D is the opposite of B. Like if you actually, again, I know this isn't super important here. If you multiply this by 26 over 26, you would get negative 27 plus 52 all over 650, which is 25 over 650, which is 1 over 26. So it looks like B and D are opposites of each other, which we could probably find out in some other calculation if we move along here. So D equals 126. Oh my goodness. Sorry for the terrible numbers. I didn't mean for them to be quite that terrible. So then if we integrate this, we get the integral of 2 over 25 over x plus negative, sorry, you can't quite see that, negative 1/26 over x minus 1. And this is the thing I was talking about before, the cx plus d over x plus 25, we have to break it up. We're going to break it up as the cx, which is, C is terrible here, the negative 27 over 260 times x over x squared plus 25, and the d, which is 1 over 26 over x squared plus 25. So whenever you end up integrating a cx plus d over x squared plus something, we always break it up as cx over the bottom plus d over the bottom. We always do it that way. It's not that we choose, we can't do it any other way. Like there's no choice. So then to integrate that, we might as well finish it off. So I'm going to rewrite this as the following. It's going to be 2 over 25 integral of 1 over x minus 1 over 26 integral of 1 over x minus 1 minus 27 over 650. That's what that doesn't look like what I wrote there. Sorry. Over 650 integral of x over x squared plus 25 and 1 over 26 integral of 1 over x squared plus 25. So then the rest of this is just using our rules. This is going to be 2/25 natural log of the absolute value of x minus 1/26 natural log of the absolute value of x minus 1 minus 27/650. This is the one that requires the u sub. And you'll end up getting 1/2 the natural log of the absolute value of x squared plus 25. Because if you think about the derivative of this, the derivative of this is 1/x squared plus 25 times 2x, and then the 1/2 cancels the 2 to give you just an x of that. And then this part's going to be the arctangent one. This is going to be 1/26 times 1/5 arctangent of x/5. Let's see. So that's how in a partial fractions problem where you had an irreducible quadratic factor is going to typically go. The other thing I'll say, we won't do this one, but I'll just point out that the other thing that could show up in a partial fractions problem is something like this. We have the integral of, say, like 5x plus 1 over x cubed minus 8x squared plus 16x dx. If we do this one, the denominator ends up factoring as x times x squared minus 8x plus 16, which is x times x minus 4 times x minus 4. And when you do this partial fraction decomposition with a repeated linear factor, you have 5x plus 1. Sorry. You have to write this as your initial integrand equal to a over x plus b over x minus 4 squared plus c over x minus 4 to the first. And then you would find a, b, and c. So when you have a repeated linear factor, you have to have that highest power and every lesser power. All right, that's all I got. Good luck on your exam tomorrow, if you have an exam tomorrow. Well, first. You're very welcome.